Welcome to AI Peer Review, the show that gives you a shortcut straight into the most compelling breakthroughs in machine learning research. Today, we're deep diving into a novel architectural tweak called Bridge. It tackles one of the bigger efficiency headaches in scaling LLM inference.
Yeah, it's a really interesting one. When you look at high-performance LLM tasks, especially complex stuff like, say, math competition problems, you definitely need to scale the compute power.
Right, and you usually scale in two main ways.
Yeah.
Making the generation longer, like chain of thought, or just asking for more answers at once, that parallel sampling.
Exactly. And that parallel sampling, where you ask for, say, $dollar responses simultaneously, that's where the inefficiency often creeps in.
Because traditionally, each of those knowledge generations just runs in its own little world, right?
Yeah.
They're parallel, sure, but they don't share any information.
Total silos, even though they all started from the exact same input prompt, which is kind of crazy when you think about it.
It seems like a massive waste of potentially useful insights one path might discover.
Totally. Imagine like 8 engineers solving the same problem but in separate rooms, not allowed to talk. Any breakthrough one has stays locked away.
Okay, so this paper we're looking at introduces Bridge. That stands for Batch Reasoning with Interdependent Generations.
Yep. And the core idea is to rethink that batch of LLM hidden states, not as separate slices, but as one holistic, interconnected tensor.
That sounds like a pretty fundamental shift.
Yeah.
And they claim Bridge achieves this interdependence without losing the speed of parallel generation.
That's the big claim. Full parallelism, but with shared information flow. And the headline result is, well, pretty eye-catching. Up to a 50% relative mean accuracy gain when combined with RLVR.
Okay, RLVR reinforcement learning with verifiable rewards. That's basically rewarding the model if its final answer is provably correct, like in a math problem.
Exactly. It's a training method. But Bridge makes the underlying generation process itself much better before you even apply that reward signal. It helps the model find those correct paths more consistently in the first place.
Okay, gains that high usually come with a cost. I'm guessing this adds a lot of architectural complexity. Or parameters.
That's honestly the most surprising part. The cost is minimal. We're talking only a 2.8% to 5.1% parameter increase.
Seriously, on models like DeepSeek or Llama?
Yeah, on models like DeepSeek R1 Distill Quinn 7B and DS Llama 8B, it's incredibly efficient for the performance boost you get, especially post-training.
All right, let's dig into the weeds a bit. What's the standard limitation they're breaking here? Remind us about the standard transformer forward pass.
Okay, so the hidden states in a transformer are typically represented as this 3D tensor, right? You've got batch size, Byler, sequence length, Zellers, and the hidden dimension dollar.
T by S by D. Got it.
And all the standard attention mechanisms, like self-attention, they work along the sequence length axis, the Zeller dimension. That's how a token looks back at previous tokens in its own sequence.
And crucially, the batch dimension, Byler's kept strictly separate. Each sequence in the batch is independent.
Right, and that usually makes perfect sense. If you have a batch with totally different prompts, you need that separation. That's why we use layer normalization, not batch norm, in transformers to stop interference.
But, and here's the Bridge insight, I guess. When you're doing parallel sampling for the same prompt, that batch isn't different at all. It's uniquely homogeneous.
Exactly. All null sequences kick off from the identical input tollers, so the whole reason for that strict batch independence kind of evaporates.
Which means there's this massive untapped potential for information sharing just sitting there.
Precisely. Mid-generation sharing becomes feasible, even desirable.
Okay, but hold on. If you start letting these parallel streams talk to each other, isn't there a risk? What if one sequence goes down a completely wrong path? Does Bridge risk polluting the whole batch with bad signals?
That's definitely the core challenge they had to address. How do you share the good stuff without amplifying the noise? The success of Bridge suggests the benefit of sharing successful steps outweighs that risk.
And it's different from some other methods, right? Like groupthink.
Yeah, that's a good point. Methods like groupthink or hogwild. Inference, they often use multiple processes, but funnel everything towards synthesizing one really good output.
Okay.
Bridge is different. It uses non-parallel processes to generate non-high-quality outputs simultaneously, but those outputs are interdependent. The goal is to improve the quality of the whole set of answers.
All right, let's unpack the mechanism then, the Bridge block. How does it force this collaboration without messing up the parallel computation?
So they insert this new block, the Bridge block, right after each standard feed-forward block in the transformer architecture.
Okay.
And here's the key conceptual flip. Standard self-attention looks along the sequence length axis. Bridge attention flips 90 degrees, effectively. It operates over the batch axis.
Whoa, okay. So instead of a token attending to tokens that came before it in its own
Yeah.
sentence, it attends to the tokens generated at the exact same time, but in all the other parallel sentences.
You got it. It's like applying attention to a different slice of that 3D tensor. For each token position, the queries and keys for the bridge block are calculated, allowing tokens at that current time step across the entire batch to attend to each other using that vital times D slice.
That sounds computationally interesting.
It is, and it's actually quite similar to a technique called axial attention that you sometimes see in computer vision, where they apply attention along different axes of a 3D tensor like an image. It's like they're treating the LLM batch almost like an image being decoded.
Okay, but back to the noise problem. How do they control what information gets shared? There must be rules. Masking.
Absolutely, strict rules. They detail this in their figure too. The attention mask ensures two things. One, attention only happens between tokens that came from the same original prompt. Seems obvious, but important. Two, tokens can't attend to tokens from sequences that have already finished generating, hit their stop token. This keeps the parallel structure intact and ensures tokens only attend to concurrent tokens. It maintains that Markovian property.
Keeps information flowing within the relevant group at the relevant time.
Precisely.
I also saw they don't use positional encoding within these bridge blocks. Why skip that?
Good catch. That was deliberate. Omitting positional encoding makes the bridge block invariant to the position of a sample within the batch.
Meaning it doesn't matter if a sequence is the first or the fifth in the batch?
Exactly. This makes the architecture much more flexible and robust if you change the generation with the number of parallel samples.
Okay, that makes sense for versatility.
And another neat side effect, because bridge attention only looks at the current time step across the batch, it doesn't need to maintain its own key value cache like standard self-attention does.
Oh, interesting. So it's simpler, memory-wise.
Yeah, keeps the overhead down. It's a lean addition overall.
That low overhead fits nicely with the training story. They emphasized low cost and efficiency there, too. How do they actually train this, especially with reinforcement learning involved?
They use a pretty efficient two-stage process. You can see it laid out in their figure 3. Stage 1 is basically a quick warm-up using supervised fine-tuning, or SFT.
Okay.
They generate a bunch of responses, like, say, 8 answers for each math problem in a dataset like GSM-8K. They filter these for correctness. Then they train only the new bridge parameters, not the whole model on this filtered data set for just a few epochs, like 5.
So you're pre-teaching the bridge blocks how to communicate effectively using known good examples before throwing them into the RL loop.
Exactly. It gives them a good starting point. The ablations showed this warm-up helps, though it wasn't strictly essential.
And then stage 2 is the reinforcement learning.
Right. Stage 2 uses reinforcement learning with verifiable rewards, RLVR, specifically using a variant of the GRPO objective. GRPO is Generalized Policy Rejection Optimization. It's a way to fine-tune models based on feedback or, in this case, whether the answer is correct.
Now, how does adding bridge change how GRPO works? Because standard RL objectives usually assume the different trajectories or rollouts are independent, right?
That's the crucial point. The standard GRPO math does assume independence when calculating things like the policy ratio or the KL divergence term. But bridge fundamentally breaks that independence.
Because the architecture itself now links the policy across all the sequences in the batch.
Exactly. The bridge blocks physically connect them. So when you calculate the advantages, the rewards, and the gradients for the update, they become intertwined across the whole group.
So it's not like dollar separate updates anymore. It's more like one big collective update.
That's a great way to put it. If one sequence finds a good path and gets a positive advantage, that signal gets shared via the bridge blocks. It essentially boosts the learning for all its parallel partners.
And presumably if one path fails badly.
That negative signal also gets shared, acting as a stronger deterrent for the whole group. They're learning together, benefiting from each other's successes and failures in real time during training.
Okay, this collaborative learning sounds powerful. Let's talk results. What did this actually achieve? You mentioned the 50% gain.
Yeah, so the performance gains were pretty consistent. Looking at accuracy, specifically pass at 1, getting the single best answer correct. Bridge consistently came out on top across a range of 7 math and reasoning benchmarks. Stuff like Math 500, AMC problems.
And that 50% figure.
That was the relative gain using the DS-Quinn 7B model. Comparing Bridge combined with RLVR against just using RLVR on the baseline model without Bridge, Bridge added another 50% improvement on top. That's referencing Table 1 in the paper.
Okay, but the skeptic asks, did they just get better results because they added more parameters? Even if it's only a few percent.
Fair question, and they addressed it directly. They ran a baseline called p-match.
They match.
Yeah, they added standard MLP layers with the exact same number of parameters as the bridge blocks, placed in the same spots in the architecture.
Ah, so a direct comparison for parameter count.
Right, and the result, the p-match baseline gave much smaller, more inconsistent gains and sometimes even hurt performance.
Okay, that's pretty convincing then. The improvement isn't just more parameters, it's how those parameters are used specifically, the interdependence mechanism.
Exactly. It's the architecture, not just the parameter count.
What about versatility? You mentioned the lack of positional encoding helps with changing the generation width, not a dollar. Did they test that?
They did. That DSQ-17B model, for instance, was trained with a width of 4, but when they evaluated it at wider settings, like generating 8 or 16 parallel responses, Bridge still outperformed the independent sampling methods significantly. Table 2 shows this.
So generalized as well, even when the test width doesn't match the training width, that's pretty robust.
Yeah, it confirms that architectural choice about positional encoding really paid off for flexibility.
Now, beyond just getting one answer right more often, did they look at the quality of the whole set of answers? Like, how consistently good were all N responses?
Yes, they used a metric called GPass at CAR. It's a bit more nuanced. It measures the probability that at least a fraction tau, like 50% or 100%, of caller-generated responses are correct.
Okay, so low tau would measure if you get at least some correct answers coverage, while high tau, like tau-tau-toler, measures if all tau answers are correct.
The consistency.
Exactly. And their figure 4 shows the results. Bridge achieved higher GPass at 8 values, pretty much across the board for different levels of tau.
So it improved both coverage and consistency.
Significantly. For example, it really boosted the rate at which all 8 responses to a problem were correct. That's GPass at 8 with tau-toler.
Which means it's not just finding one correct answer more often by chance, it's genuinely making the generation process across all parallel threads more reliable and correct.
Right. It increases the frequency of correct generation for the entire set.
So wrapping this up, it feels like Bridge offers a fundamental shift. By treating that LLM hidden state batch as this holistic 3D structure, almost like decoding an image, it changes parallel generation from isolated competition into genuine collaboration, pooling that inference compute much more effectively. That holistic view, applying attention on the batch axis, that's the core conceptual leap that unlocked these really impressive gains for such a small architectural cost.
You know, one of the most intriguing bits for me was in their analysis, I think it was figure 7, they looked at the contribution of different blocks to the overall feature norm.
Oh yeah, I remember that.
And the bridge blocks, surprisingly, contributed very little to the overall norm compared to the standard attention or feed-forward blocks.
Tiny contribution, norm-wise.
Yet, they had this massive impact on the final performance.
It's fascinating, isn't it? A very subtle change structurally, but with disproportionately large effects downstream.
Which really leads us to the final provocative thought for you, the listener. If this small, subtle architectural change, added only during fine-tuning, has such a dramatic effect, what happens if you integrate bridge blocks much earlier?
Like during pre-training, or maybe mid-training.
Exactly, as the authors themselves suggest for future work. If parallel scaling and this kind of interdependence were baked into the base model from the start, could that fundamentally change the efficiency and capability curves for building the next generation of LLMs?
That's a really exciting question. Making collaborative generation an inherent part of the model's foundation?
Yeah.
Yeah, that could be huge.
Something to definitely keep an eye on. Okay, that's all the time we have for this deep dive. We'll see you next time on AI Peer Review.